Alright, so once we find every single displacement for each possible adjacent pair, we can then add them all up to get our net displacement. Remember, net is all the positives minus the negatives. Here's the sum, 396. Now, to go from position to velocity, suppose we want to change that position in timetable to velocity in timetable. It shows the same exact motion. To start with, our velocity table is 1 point shorter. Right? It's not the same amount. That's because you have to have two pairs to get it. So the point on the velocity is calculated from the first and second points. The first velocity is delta x over delta t. So if you did 5 divided by 2, you're going to get 2.5. The time is 1 second. Average of the two times, because the velocity is 2.5 meters per second, happened at some time between t equals 0 and t equals 2 seconds. So it's the average of these 2 points. Same thing. Final, initial, divided by the average. Second point, and then it's going to continue just to go on. Average is 4, and 6 is 5. Alright. Suppose we want to change the position. Suppose we want to change the velocity and input it into a position versus time table. To start with, the position table has the same number of points and the same times as velocity. Starting position must be specified for us, otherwise we're going to have to assume that it's 0. Okay. So if it's not given to us, we're going to assume it to be 0. That's all we can do. Next, we find the displacement, exactly as before. So it's going to be velocity times time will give us displacement. Get the two velocities, get the time difference, and then multiply the average velocity by the time difference. Each displacement is added to the previous position. See if you can pause here and complete the table. Okay, so hopefully you did well with that. Problem with tables is, yeah, that took forever. I mean, we're in the second video here. It's a lot of calculating. It's hard to just look at the numbers and see what's actually happening. It's difficult to determine displacements and positions from velocity and timetable, and changing a position table to a velocity table takes a lot of work in a controlled process. We don't know what exactly happens between, like when we took the instantaneous velocity at 3 seconds, we think it happened at exactly 3 seconds because we took 2.9 and 3.1, averaged them together, and we got 3. But what about at 2.993 seconds? Then what exactly was the velocity then? So we don't know for sure what happens. It's our best estimate. We don't know the object moves during those times, before the table starts or after it ends. Why do we have to learn about them if they're so annoying? When we do an experiment to see how an object moves, the result of the experiment will always be a position in timetable or velocity in timetable, just like we did with the carts. Because this is a motion experiment can give us, we need to learn how to deal with tables. Motion diagram. Easy to make and read, but not good if we have to do math. So we know how, we've seen motion diagrams, so those little dots, it's kind of like a strobe light effect. We can make a table of motion into what is called a motion diagram. A motion diagram is a number line with dots next to it. Each dot represents the object at certain times. The dots are drawn at regular times, 1, 2, 3, 5, 10, 15, whatever, as long as it's interval. We can change a position and time table into a motion diagram if the table has equally spaced lines. So here we go. We have our lines, our number line with equal spaces, and then this simulation, as the red car is going, a red dot is being dropped every 1 second. Boop, boop, boop. Same thing for the green one. Let's start it over. Boop, boop, 1 second. Looking at this animation, can you see which one is going faster? Obviously it's green. It's covering more distance in the same exact amount of time. But they're both moving with it at a constant velocity. They're not speeding up. Everything is equal between these two dots. Red car on top is going slow, the green car on the bottom is going fast. Both motion diagrams are every second. Here's our position and timetable for the red, position and timetable for the green. Which one's easier to look at? I think it's the motion diagrams for sure. Blue car is speeding up. The dots become farther apart as the car goes faster. The purple car on the bottom is slowing down. The dots become closer together as it slows down. Let's watch that one more time. There we go. What about direction? The red motion diagram on top. Is the object moving right or left? I don't know. Green motion diagram on the bottom. Is that going right and speeding up, or left and slowing down? Point is, we usually draw arrows on each dot to represent the direction the object is traveling. The arrows become longer as the object's speed increases. The arrows become longer as the object speed increases. Important. Here we go. Constant velocity, green. All arrows are going to be the same. Blue started out with small arrows, and now we're increasing. Purple, pink, however you see this, we are slowing down, so we start out with a big left arrow, and then it's getting shorter. If an object changes direction, the dot drops down the same way that we drop down to the next line when we read text on a page. Well, kind of. Point is, you go one line, and then the next line, and then the next line. We obviously don't read like that. Car slows down over 5 seconds, stops for 5 seconds, and then speeds up for 5 seconds. Calculating average velocity, we already know it's final minus initial position divided by final time minus the initial time. Get the time interval between the and the end is 1.2, divide displacement by time is 4.5. Calculate instantaneous velocity, say at 1 second, exactly 1 second, here we go. Get the displacement, so it's going to be 3 point here, and oh, here we go. I didn't see it went past 4. So it's going to be 4.8 minus this 3.1. So we're taking the 2 dots between. Here it's going to be that. Get the time interval between the dot and after the dot. Here it is 1.1 minus 0.9 is 0.2 seconds. Divide the displacement by time and you get 8.5. So the advantage is it's easier to see if the object is speeding up or slowing down than looking at a table, but we still really don't know what happens between the dots.